it was simple enough. It wasn't really an issue. But just to make sure, you know, it's good to start simple and then escalate. So to make sure that you understand how this works, because yesterday's was a simple linear example. I'm going to finish the example that we started yesterday. And remember the significance of it. It's the analysis of the repeated doubling approach. And so by the time we come up with an answer, which would be an order of growth, we would then be equipped to make a comparison. And hopefully you can make the right comparison. You know, sure. Sorry?
You were saying you were making the intro, so you plugged it out until you're okay.
Oh, no. The whole idea is that it can't see the board if it's too small. So just do it. All right. So yesterday we had, after the simplification of the three cases, we had, was it 1? If n equals 0? Yeah. And then 8 plus, well, I'm calling it, can I? Okay, fine. So you'll have continuity in your notes, T2. This is n minus 1 over 2, yes? Good. So then we said, okay, we need to construct this recursion tree. And I showed you what that input size was going to be, but some people came up to me afterwards and said that wasn't clear how I got that. So let me illustrate that one step so you can see what's happening. Notice that if I wanted to, okay, for n bigger than 0, we're saying this is 8 plus. When I want to figure out what T2 of n minus 1 over 2 is, assuming this is bigger than 0, that's going to be 8 plus T2 of. Now what you need to do is substitute this for n. So that's going to be n minus 1 over 2 minus 1 over 2. Okay? And when you do your simplification, that's going to be n minus 3 over 4. So that's where that came from. So picking that up, with our recursion tree, and I'm gonna save this space here. I'm gonna draw my tree over on the right hand side, but I'm gonna save this space for when I want to work out what the value of d is in terms of n. Right? Remember, we want to do this very systematically. So we will draw a recursion tree. And what we're seeing is that overhead is just 8. And there's one child. One child of that node because there's only one reference to the function itself. Now this part would have required a little bit of I don't know, a mix of experience and experimenting. But what I suggested to you is that if I carried on with this process, you'd have seen, for example, the next one would be n minus 3 over 4 minus 1 all over 2. And you can see that n minus 3 over 4 minus 1 would have been n minus 3 minus 4 over 4, right? So that would have been n minus 7. And the denominator would have been 8. So when you, this is kind of the pattern testing, and you basically would essentially rigorously what you're doing is a proof by induction. But operationally, what you'll be saying is, well, the pattern looks like this number is always 1 less than that one. And if this one's a power of 2, then this numerator will be that same power minus 1. You can test it and confirm for yourself that it actually works. But that's essentially what I'm doing when I write that expression down. All right, so that's my general term. And where does this stop? It stops when the input equals 0. And at that point, it's just 1 plus nothing. So we had that yesterday, yes? Okay, now you've seen it again with a little more clarity, I hope. Now what we need to do is figure out how deep is this tree, because clearly, if I'm going to add up all the overheads, what I see is a bunch of 8s, and that's just fortunate that there are constants, but it's 8 for all the nodes above this leaf level, and then just 1 at the leaf level, right? So in order to give this a name, this level, that I can figure out where this level is, I'm going to give it, this is what I've been doing, I've been calling this level D, D for depth, D to represent the depth of the tree. So I'm saying I have a depth D tree, but I don't know what D is yet. And how do I know what the value of D is? Well, D is going to be defined by that level when the input size becomes 0. So D is that very specific value of I, such that that input size is matching this condition for base case. Which in this case means that I would have n minus 2 to the D minus 1 over 2 to the D must be equal to 0. If my condition had said something like less than 1, then this inequality would have been an inequality and would have said less than 1 here. If it had been less than 2 or less than some constant or less or equal, whatever that condition is, that's what this would be. And what's on the left-hand side is whatever that general expression is for the arbitrary depth term. Now, of course, when you simplify this, what you get, just multiply by 2 to the D, that goes away. This is n plus 1 minus 2 to the D. And so what this means is that D is log base 2 of n plus 1. Right? You got that. That's excellent. So now what's the final answer? T2 of n is the sum. Remember, we need to sum all these overheads. So we'd start at level 0, I equals 0. We'll go down to how many times do we have an 8? It doesn't actually go to I equal D. What do you say? V? Oh, I don't know. The last level where you'll find an 8 is the one above the level D. And if they're going up by, the numbers are consecutive, so the level above D must be D minus 1. So all of these had 8, and then the last one was a single one. Yes? Yes? It's divided by 2 to the D. You're wondering what is that expression there? It comes from here. Plug I equal D. That was a general term. There's a 2 to the I here, yes? So plug I equal D in, that's a D. I don't know if that's clear enough. I'm not sure. I don't know if you want to. It's clear that's 8D plus 1. We already figured out that D was log of n plus 1. And usually what we want, I don't want to get you in the habit of trying to find exact solutions, because for most practical situations, that's nigh impossible and not necessary, thankfully. So we don't really care that it's 8 times log of 1 more than n plus 1 more. that would give us exact, you know, this is great for checking if you actually have the right answer. You can actually substitute real numbers of, you know, values of n in here and do your little test to see, in fact, that you get the right answers. Of course, the way that this was defined, we had some assumptions about integers and so on. You have to take those into account. But once you do that, remember that this is the worst case scenario. So it's applicable only to those n's that cause the recurrence to alternate between the even and odd case every time. But if you were to plug in any one of those specific n's and plug it into this exact formula, you ought to get exactly the same answer as if you had run this recurrence down to the base case and then summed up the answers. As I said, we don't care about the exact answer. What we really care about is order of growth. So now we have an answer to the running time, to the question of what is the running time of the repeated doubling approach. Remember where we came from. What one problem? It was what one problem? It was to implement multiplication on a piece of hardware that didn't support multiplication. It supported addition, subtraction, left shift, etc., right shift, etc. We had one approach which was multiplication and repeated addition. And when we analyzed it, whether they implemented it recursively or iteratively, we got order n. And although in one case the constant was like 2 and the other one was 3, look, both of them were order n. We don't consider one better than the other, even if the constant was technically smaller in one case than the other, right? Those constants are somewhat artifacts of the language in which we express the algorithm. So we kind of want to suppress them. What matters, though, is in that case, if something is order n, that means that if my input size doubled, I would expect the time it takes to approximately double as well. That's what it means to be order n, because the running time is proportional to the value of n. What's happening here is that this running time here is log n. Now this one is the third approach, which was, don't look at it as repeated addition, but where the opportunity when y was even, you would double x and half y. So that's what I mean by the repeated doubling, because you keep doubling when you can, and of course y was halving. And what you guys saw from before is that intuitively that seemed like it would end up being faster. What you're seeing concretely right now is that what I have here is an actual function that tells you exactly how long this is taking. And importantly, what you can see is, in order to get an increase in log n by even 1 more than it used to be, how much would I have to change n by? Can you put some precision to that? Yeah, let me ask the question again. All right, so suppose for a given n, yeah, we have that log n comes out as some number. If I want to make that log n be 1 more than it used to be, how much should I have to change the original n by? What do I have to do to the original n to make, I have to double it. So in other words, if at n equals 100, this took 1 millisecond. What's my unit of 1 here? It might be a microsecond. For it to just take 1 single microsecond, if I were to double the n to 200, it would only take 1 microsecond more. In that, I'm just kind of making up the scale there. But the point is, doubling the input only incremented the output by a constant amount. So that means that if you have very large inputs, potentially, and you have a logarithmic time algorithm, chances are it will be running lightning fast. You won't notice that the input got much bigger unless it really was geometrically increasing. You want to keep that in mind when you're, you want to keep that in mind in general. Logarithmic time algorithms are nice and fast. I hate to boil this down to foolishness like your grades, but if you're overly focused on that, then that's one thing to keep in mind when you're trying to figure out how to pass those hacker rank tests, because that's often the difference between passing everything, all the test cases, and only the small ones. If you have a running time that's order n, just a quick word, your hacker, I mentioned this to you before, but I'll bring it back to now that you have been doing some of them. You have about 2 times 10 to the 7 operations before you run out of time. It doesn't matter what language you use. That's how HackerRank have tried to calibrate the running times given to each language. So Python is given 10 seconds, but that kind of translates to roughly 20 million arithmetic operations, roughly. So what that means is that if you have an input size of something like 1 billion, right? That means that you can only afford, if you have an order n time algorithm, that means your output is going to scale according to that input. When you put in 1 billion, you really only have 10 to the 7 divided by 10 to the 9 seconds. So that's 1/100th of a second for each unit of input. That means that whatever you're doing in your code, if that can't finish running in 1/100th of a second, you're going to run out of time. Now, maybe what you're doing is essential. Like in your loop, you look at it and every step is needed and there's nothing you can do about it. And that's taking more than 1/100th of a second. Then that might tell you, maybe I need a better algorithm. Something that's not order n, but maybe log n, for example. Something that somehow doesn't scale proportionately, but somehow is much faster. In your first assignment, they had questions that accumulated things. Those of you who wrote loops to accumulate, you were producing code that would run according to the number of steps needed to do the complete accumulation. If you use a formula instead, you get the final answer in 1 step with a fixed number of arithmetic operations. That's a comparison of an order n algorithm, where the number of steps was proportional to the size of the input, versus an order 1 algorithm, where you just had no matter what the input size was, you had a formula for it, bam, in 4 instructions, you were done. Regardless of the size of n, you had 1 formula, gave you the answer. The other approach where you're accumulating in a loop, the number of steps you needed was proportional to that size, so that's an order n algorithm. You see the difference between an order n and an order 1? Well, 1 passes all the test cases and 1 does not. Time's out. Time's out. So if I've done my job right, that's what will happen. Sometimes everything's not perfect. Anyway, what we're seeing here qualitatively is that this algorithm, repeated doubling, is much faster than the repeated addition. Yes? Good. I want you to keep that in mind, because that repeated doubling algorithm is really powerful. In the tutorial next week, you'll see one applied to finding powers, and then you'll see how we can use that to find things that you would not have dreamt were powers. Expressing those computations. Question?
So how would you be able to reduce it to, let's say, a log n rate instead of just an n rate?
Okay. The question is, how in general would you go about reducing your order n time algorithm to an order log n time algorithm? And the answer is that's not always possible. So that's a quick answer. It depends on the problem. And what we're going to do is kind of examine some of the, that's a great question. What I'm going to try to do is examine what are some of the features of this particular algorithm that led to the log n performance that will help you keep an eye out for when you have that opportunity. So what do you notice about this recursion tree here that led to it being log n growth, order of growth? What about that fraction? The recursive call was halving the input size, whereas one that had repeated addition, the recursive call was only reducing the input size by 1. But in the context of the tree, what happened? We still had a tree that looked linear like this, but notice that the height of this tree was much, much shorter. In other one, I would have had a node for every value of n, for whatever value of n is, that's how many nodes I would have had, plus 1 more. In this one, what this is saying is I'm going to have only logarithmic many nodes. And so that's ultimately why the running time ended up being lighter. From the perspective of the code, what about that code caused this running time to be so much shorter, this tree to be so much shorter? It had to do with how the recurrence diminished, how the input size decreased from one step to the next. that clear? Whoever asked the question?
Yes, sir. I understand.
Okay, thank you. Good. So now what I want to do is kind of give you a different kind of example that doesn't look as trivial as these, because these in some ways, you know, this is called a recursion tree, but so far you've only seen something that looked like a ladder or a list. It's called a degenerate tree. It doesn't really fan out. What if you had a different recurrence? I'm going to call this one T. And for now, I'll just leave this as something like that. But here I'm going to put I'm keeping this, I don't know, maybe this is too simple. Should I, let's make this a little more interesting. Did you say 5? That's even more interesting than 5. So now the overhead changes. So far you've always seen constant overhead. I don't even think that it's always constant. And now we have 2. We're gonna have, so each node is going to have 2 children, right? So the question would be use a recursion tree to find a closed form expression. Now, if I sketch this tree, how do you expect it to look? I mean, let me do the hard part. I'll start it. The overhead is going to be n. And now you do the easy part now. 2 what? 2 children. And what's the name of each child? It's going to be n over 2. And the overhead is what? Not quite. N over 2. Yes? Yes? Yes. So, when we write n here, that n is not living in abstraction in a vacuum. That n is scoped where? Where does n come from? This here. This n here is what defines, in computer science we say it scopes it, right? It's that n that says, look, all references to n on the right-hand side are referring to whatever value is inside those brackets. So when we're dealing with t of n over 2, then this value over here is going to be, this overhead is going to be n over 2 because that's what's in the brackets. It also then means that its 2 children okay. Kind of run out of space here. What does a generic level node look like? N over 2 to the I. Good.
Can the camera be moved, please?
I think I can't see. Sorry? Yeah, I think they can't see what's going on. The people who are not here in Caveville. Yeah, and it's also, if it's inverted, that means I can't see, right? Or does it invert on their end? Flipped again? Okay. I heard somebody saying something, so I assumed that they couldn't see. Okay, so the leaf level, I've just written this thing here, less than or equal to 1. It's something we'll figure out. We will have to figure out how this happens. That's what will determine what the depth is. What's the overhead at the leaf level? 1. Now let's get a handle on what the costs are. Remember, what you now need to do is to find what T of n is, you need to add up all the overheads in the entire tree. So the best way to get a handle on this is, I recommend, add them by levels.
Sir,
Yes. Go ahead. Is that Cave Hill trying to ask a question? Please go ahead.
Right, sir. I was just saying that the rightmost side of the board was difficult to read.
Yeah, I have my tech guy trying to sort that out here. Didn't know what to call him. My video assistant. Yeah. Yes. It has to be high enough. That's the problem. Where? All right. I'm gonna press on. Try to take snapshots if you can, if that helps. Okay. Normally, and you can do this in your notebooks, on the right, I would sort of capture what the sum of the overheads is at each level. And then I'd write down the sum across all those levels. So I won't be able to document it on the right because I'm out of board, but I will write down the expression on the left in the other panel. All right? So I strongly recommend you keep the annotation the same. You know, this is level I equals 0, level I equal 1, I equal 2. This is generic level I. This is our I equal D. So we have 2 parts to solve. We can write down, first of all, T of n is going to be the sum starting at level 0 up to what level? D minus 1. It's a level up the leaves, right? And what am I summing now? So what I want you to bear in mind, all right, so at an arbitrary level, n over 2 to the I is for 1 node. You have to ask yourself, how many of these nodes do you have? All of them will have the same overhead, right? You notice that? You're going to have 2 to the I of them. So what I have here is 2 to the I nodes, and each of them has an overhead at n over 2 to the I. So I'm summing those from 0 to D minus 1, and then at the leaf level, I have a bunch of 1s. How many 1s do I have? If the level is D, you just said I have 2 to the I nodes at level I. So if the level is D, I have 2 to the D nodes. Does that make sense? Yes? There's no 2I up there. Yeah, the big difference.
The n over 2 to the I is outside of the summation.
No, no, no. Multiplication is precedence over summation. So that's the term. Okay, so all of this is being added. Plus, it wouldn't make sense because I is scoped by the sum. Yes, you can. 2 to the d times 1, not I. 2 to the d times 1 is not part of the summation. That's the leaf. Here, let me annotate this for you. These are for the internal nodes. And this accounts for the leaf nodes. Does that help? And the number, each of them is a pair of products, right? The number in front is the number of nodes, the number beside it is the cost per node at that level. So I had 2 to the I nodes at level I, and each one cost n over 2 to the I. At the level D, I had 2 to the D nodes, and each one costs 1. Okay, so now I'm going to do the algebra and simplify. Well, this just turns out to be sum from I equals 0 to d minus 1 of n plus 2 to the d. And so, of course, this is nd plus 2 to the d. Now, all that remains is for us to figure out what d is. So here we go. To find d, we want, now because this base case is an inequality, naturally when you solve it, you're going to get an inequality. Naturally, you're going to get something like d greater or equal to something. But because of how d is defined, d is the leaf level. So it would be the earliest integer. D is obviously an integer. So the interpretation of when we have that inequality that we're going to get of what d really is the earliest integer that satisfies that inequality. Okay? So here we go. I'll write it up here. We want the earliest or smallest integer that satisfies the inequality, which is the generic input size, that's n over 2 to the d, has to satisfy the base case condition, which is less than or equal to 1. And if n over 2 to the d is less than or equal to 1, that means, okay, which then means that d is greater than or equal to divide by 2. There's no divide by 2. So the earliest integer that's going to satisfy that, of course, is the ceiling of log n. We're not going to worry too much about sticking to these ceilings and floors. We're just going to pretend that it's the actual analytic value. It will keep our computation simpler without changing orders of growth. But if you ever are double checking yourself to make sure you got the right function and you're trying to plug numbers in, beware that we did make that assumption, that approximation in some cases. So if that ever occurs to you, you're like, wait, but my recurrence, I solve it, and when I plug it and I don't get the same answers, that's probably why. Okay? But it doesn't change the order growth. Okay. So that means that, I should have just wrapped it up right here. So what's my order of growth for T of n? So T of n, which we got to be n times d plus 2 to the d, that's n log n plus 2 to the log n. And this is what I'm saying. I want to ignore those ceiling because this is clearly a perfect power of 2. But if we're just 2 to the log n without the ceiling, what would that have been? For just, right. So this will be n log n plus n. And if I want the order of growth, which one dominates? N log n. Any questions? All right. Now for simple, managing okay?
Yeah, just trying to type now.
Okay. For simple enough recurrences, you can apply this, draw your tree, solve it, and you get your order of growth. But what we want to do now is kind of look a little bit at the pattern behind this. And it turns out that there is some generality that we can draw from this that can enable us to take some shortcuts. And shortcuts are handy, especially when you need to be able to do this quickly. So here we go. A couple things to observe. What caused each node in my tree to have a branching factor of 2? The concept beside the T. So this 2 is what determines the branch factor. Yes? It determines how many children each node has. That's what I mean by branching factor. Say yes. All right. Okay. What determined how deep the tree was? And is an input into what? But what made it become log n? Maybe on another tree that we did, the very first tree was depth was n, it was decreasing. So what part of this expression here controls how deep it's going to be? This factor of 2 you're dividing by, right? Okay. So those two things are essentially controlling. The one outside is controlling how bushy my tree is, and the one inside is going to control how deep the tree is. At the end of the day, you always need to add up all the overheads anyway. So here's what we want to do. Suppose I could generalize those two things. I'm going to call the number of nodes that each child has A, and the ratio by which the input size decreases, call that B. Do you see that even if I was dividing by, say, for example, 3 or 4 or 10, what would have happened is that this value here would have changed. Is that 2 to the D would have been 2 or 3 or 4 or 10. And no matter what would have happened, we would have ended up with a log. It just would have changed the base. It would have been log base 2 or log base 3 or log base 10. But no matter what, it would have been a log n height, just different base. And remember that when you change a base, that's just, log n base 10 is just log n base 2 divided by log 10 base 2. Log 10 base 2 is some number. So if I'm going to be worried about orders of growth, those constants are going to be immaterial. And so the base that I'm dividing by repeatedly becomes immaterial. What's important is that I am dividing by something bigger than 1. And because I'm dividing and that's how it's reducing, that's what gives me the log n depth. So as long as I'm reducing by some constant factor bigger than 1, I'm going to have a logarithmic type depth. Okay? So now what we want to do is try and get a handle on just how much the order of growth is going to change. What I hope you can see is if I have, okay, in this case, let's look at what happened. The cost of the nodes at each level ended up being the same as the first one. Notice that. So what was happening is that the rate at which the number of nodes were expanding matched exactly the rate at which the input size was diminishing. So they kind of canceled each other out, and every level ended up contributing equally to the total. Right? And that's how come I ended up with n log n. That's going to be a general pattern. That's going to be one of the cases of 3 that you have to look out for. Another situation could have been, not in this case. Suppose that had been like a 1 or a 5, as we originally were thinking to put. What would have happened? Well, this would have been, 1 and, okay, let's just work with 1. This would have been 1, that would have been 2, right? 2 ones. That would have been 4. Okay, when you add up all of those, the 1, the 2, the 4, the 8, the 16, those are consecutive powers of 2, yes? What happens when you add consecutive powers of 2? You get the next power of 2, minus 1. Yes? Remember the geometric progression? Remember I asked you to learn that in your sleep? Are you dreaming about it yet? Okay, but you're still with me. If I added up all these powers of 2, start from 0, go down to d minus 1, that just looks like 2 to the d. But guess what? That's actually already taken care of. That's what the cost of the leaf level alone is. The leaf level cost was already as much as, in fact, it's more than the whole tree in that example. So in that regard, if I wanted to know what's the order of growth of this, what you're just seeing is that the leaves are dominating and the leaves just take over. Whatever the cost of the leaves is, that was the cost of the overall algorithm. So if you're looking back at these two pieces, that's a scenario where this piece dominates and the order of the growth of the whole thing becomes just that part. That's going to be another case. In fact, we're going to call that case 1. Okay? The one that we actually had was going to be called case 2. And what I'm putting together is something called the master theorem. And I'll show you that shortly. The third case would have been if all the work that I did here was more than the rest of the work that I would have done in the rest of the tree. That's going to be case 3. Now, when that actually happens, it's a little bit technical because it's not arbitrarily large functions. Not any function is allowed there. Sometimes the function you have here, when you look at what it is in the rest of the tree, those all contribute, and what you get is something else. But you'll see exactly the technicality when I show it to you. But as long as what is here is bigger than what the leaf level costs, but not too much bigger. It can only be bigger by a polynomial. So if it's bigger by some polynomial, then it will turn out that this will dominate everything else. That would be a case 3. Now let me capture that in what's called the master theorem for you. And then we'll see how to use it. We'll see how to use it on Friday. Well, I'll just write it down for you. I want you to keep those 3 things in mind, though, even though I have to erase this tree here. You have this in your notes, so you can make a reference back when I write the general case. Actually, I'm going to give you a slightly more generic so that I don't have to give it to you again. And it actually works even if I have constants here too. Normally I introduce it one step at a time. It's like, all right, here's the original thing. You can see why it's worked, why it's true. And I was like, guess what? It also works when you generalize it like this. But you guys seem to be doing really well so far. With the explanation over here. So I decided let me just just toss in the whole thing one time so that you can. If you're feeling a little uncomfortable, don't worry. You can put back the one in your head here inside, in case one for now. And you're like, all right, C0 for now. Why I'm giving this to you is that the master theorem will apply as long as the recurrence looks like this. Okay? Okay, so now, technically the original statement of the master theorem looked the way I was writing it at first. It happens to be true even when you extend it like this. So I might as well just, since I'm telling you what is true, just write it up like that. That's the thinking behind that, okay? But here's what the theorem says. Wait, where's my overhead? No, I don't know overhead. You're wondering where's the other part? All right, so the master theorem says the following. It basically says you need to do a comparison. Now remember that this is the thing that was in the root of the overhead. So this is in our previous example, this was n. And what we were doing was comparing that with the work done at the leaf level. Okay? And if you think about what was happening, let me just write it, and then I can explain it after. Here we go. So let E, we're going to call this a critical exponent. Log A base B. We need to compare I know one of three things, no, there are more than three things that could happen, but we only have answers for three of them. Okay? So, the first thing that we know how to deal with is so think of this as, this is the work being done at that original root level. This is the total amount of work being done at the leaf level. Huh? Yeah. This n to the e is the work being done at the leaf level. All right? So why is this exactly the work being done at the leaf level? Well, look at what this is. This is n to the log A base B, right? Which you know by your little rules for logs, n to the log A base B is the same as A to the log A base, log A. Come again. N to the log A base B is the same as A to the log N base B. So, remember that. But that A to the log N base B is in fact what we were figuring out is what this is. So that's actually the work done at the leaf level. Because it was a raised to the d for the number of leaves, and each one costs order 1 time. Okay? So the point is, this here is the work done at the leaf level. This here is the work done at the root level. And we're doing a direct comparison between the two. Now, case 1 is when the leaves dominate. Now, how do we say dominate in this context? We use our asymptotic notation. So we need to say, what we really want to say is f of n is upper bounded by n to the e. Now, the problem is, as you saw in our example, when f of n equals n to the e, roughly the same order growth, that was case 2. So when they're the same, then that's a different case from when one is less than the other. So now the problem is I can't just write big O, because big O includes the theta. Little O is an interesting idea. Little O, that's not how it's normally expressed. I'd have to go and see if that's actually good enough. The way that it's normally written is, so little O may very well work. But I don't want to give it to you like that because that's not, I've not checked to make sure that's equivalent. No, that's a very good suggestion. That's perfectly right. That's right thinking, but I'm not going to write it like that. Because next thing it turned out there's some tweak, some quirk, and I've given you the wrong thing. Exactly. So here's what we say is, as long as it's polynomially smaller, and that's the point why it might end up being different from strictly little o. For some epsilon, notice that master theorem gives us an answer immediately. Once you can verify the case, you have an answer. You don't work out no tree, don't need to draw no pictures, nothing, none of that. Figure out whether this is true, and you have your answer. Second case. They're the same. Same order of growth. Then the function that you're trying to figure out, T of n, has an order of growth equal to whatever the cost of the leaf is times a log factor, log n. Of course, in this case, because n to the is the same order of growth as f of n, this is the same as f of n log n. That's case 2. And then the third case, this is the one that said it's technically, so if this one is like less than, f of n is less than, work out the roots is less than the leaves. This one is the same, work out the roots is the same as the leaves. What do you think case 3 is? More, right? So you'd expect to write something like f of n is omega n to the e. Now I can't leave it like that because that's also included in case 2. So I need to write plus a little something. That symbol is a delta. And you can think of it in your head as a little something, a non-zero something. But this is not good enough because this would allow arbitrarily big functions, and when the function is too big, our conclusion will not be correct. So for the conclusion to be right, it's bigger, but not too big. So we need and. What I mean by not too big, that means it's upper bounded by something else related to n to the e. So it's still big O of n to the e plus another something. So if you can sandwich f of n between n to the e plus a little something and n to the e plus a bigger something, then you're in case 3. And what master theorem says is that T of n is theta f of n. Okay? And on Friday we'll use it. You'll see, we'll actually use it to solve the very same problem, see if we get the same order of growth. And then we can do some more. Question, yes?
Base B.
Question is, this order of growth shouldn't it be log n base b? And answer is yes and no, meaning it's to derive it, yeah, you get log base b. But once you put it in the order of growth, log base b is just like log base 2, they differ by a constant. Log n base b is the same as log n base 2 divided by log b base 2. B is a constant, so log b base 2 is a constant, so in terms of the order of growth, it's the same order of growth. And in fact, on that note, in some textbooks, sometimes when you see a log inside of an order of growth, to emphasize the fact that the base doesn't matter, you'll sometimes see them write log with no base. And that's the kind of signal to you that the base doesn't matter. We tend to just think log base 2 and keep it, so I'll write lg. Okay, so I'll see you on Friday, or if not before.
Software looking